So they give us the standard enthalpy change of formation, and I've written it in. So the best way to deal with a question like this is to write in what you are given. Okay, so definition. The formation is from its elements in standard state, so it must be that one. There's 2 moles form, so I must multiply it by 2. Second one, enthalpy change for BRF3 liquid to gas. It is again plus 44. There's 2 mole of them reacting, so we must multiply it by 2. This one is given to us, that reaction, the enthalpy change for that reaction. There's actually more than one thing happening in there. There's some atomization happening for the one, and for the other, actually both atomization happening in there. Okay, and then there's an unknown one, and this is the one that we're actually looking for. The enthalpy change for this reaction. That's what we're looking for. I've written it out for us. We have got Hess's cycle that we can apply. So that little red arrow is also the enthalpy change. So that's going to be equal to the enthalpy change for this green one going all the way around. We can calculate it. So that means the enthalpy change for this reaction is that 1212 kilojoules per mole. So this is when we have 2 bromide atoms reacting with 6 fluoride atoms, producing that bromo trifluoride reaction. If we draw that molecule, we can see there are 6 FBr bonds in each molecule. 3 in each molecule, 6 in 2 of them. This reaction is for the formation of 2 molecules. So if we divide that amount by 6, we get the bond energy for each one of those. So quite a long route to get there. But yes, so B being the answer. Number 10, also nice question. Wow. So they give us 2 reactions, and the first one is where sulfuric actually, they say the reaction goes to completion. This is actually a dissociation, complete ionization of this reaction, right? So it dissolves in water. If you don't put water with the reactants, you don't have to put it with the products. You just put the ions in there. So if something goes to completion and we know it's fully ionized, we can say the following. If we had 2 mole of sulfuric acid, there would be 2 mole of the iron and 2 mole of the hydrogen ion formed. Because it's a 1-to-1 ratio, 1 mole of this produces 1 mole and 1 mole of that. So this is dissolving. It's dissolving into that amount. Now this is what we then have for our second equation, and this is an equilibrium. As soon as we have equilibrium, we can use our table form. This means we start off with 2 mole of that HSO4 negative. There's nothing of the sulfate ion present, but because of our first reaction, there's already 2 mole of our hydrogen ions present. Remember, this is all happening in one vessel of 1 cubic decimeter. That's why I'm not mentioning even the cubic decimeter at the end of the day. So this is our assumption that we're making. Now, at the end, they tell us there's 1.988 mole of the HSO4 negative present. That means for my react, there's 0.012 reacted, and it reacts according to my mole ratio, which is again a 1-to-1-to-1 ratio. Substituting it in, now I get my equilibrium concentrations. Alright, so I worked in mole, but remember it's per 1 cubic decimeter, working in that 1 cubic decimeter the whole time. So substituting that back into my Kc formula, I get to my value. So quite a bit that you needed to do there as well. Right, that's question number 2. An ore of manganese contains 4% mass of manganese dioxide and no other manganese compounds. Alright, so I need to think about this quickly. I calculated, when I see the percentage, I immediately think percentage composition. So I did the quick calculation for the molar mass of magnesium dioxide. Alright, so of the 1,000 kilogram ore, the 1 ton, 4% is magnesium dioxide. This means 40 kilogram of that is manganese dioxide. And now they ask, what is the mass of the manganese in there? So now we need to go and do a percentage composition. So percentage composition is literally the molar mass of manganese over the molar mass of manganese dioxide. It's that ratio. And the whole first thing that we did in grade 11 times the 40 kilograms, and that gives me the mass of manganese in that whole compound. Right? So I think we could have guessed that as well, almost without doing the calculation, because it's not going to be the 40 kilograms, that's the whole magnesium dioxide. You can't have more manganese in that 40 kilograms than obviously 40, so A is my obvious answer in that one. Number 5, nice question that we have in here. They say we have a white powder and it contains both magnesium oxide and aluminium oxide. If we add sodium hydroxide, a specific amount thereof, then it totally dissolves the aluminium oxide in grams. So we can do this, and they give us a little reaction. So we can go and calculate what's the mole of sodium hydroxide that is needed to fully react with my aluminium oxide. Okay, so if I calculate it, it's a 0.2 mole. According to my balanced equation, I can see that it's a 1:2 ratio. So actually from this, we can deduce that there is 0.1 mole of aluminium oxide present in that X amount of grams. So nice, that's given. Or not given, it's deduced. Now, they say if you take that full sample and you add that 800 cubic centimeters of a 2 molar hydrochloric acid, and that's just enough to dissolve all the oxides, so both oxides in there. Well, we've got a bit of information here already. We know that there is 1 or 0.1 mole of aluminium oxide in there. So if we just consider the top reaction, and over here I went and I calculated the amount of mole hydrochloric acid. So it reacts in a 1:6 ratio. So in essence, 0.6 mole of hydrochloric acid is being used up in my first reaction with, if you consider it as 2 separate reactions. I know it's happening all in one container, but if you consider aluminium oxide taking some of that hydrochloric acid out already. And because we know the amount of aluminium oxide, we can say, right, the aluminium oxide will use 0.6 mole of hydrochloric acid up. So in that reaction, we can think of it as an excess. This means there's 0.1 mole of acid, 1 mole of acid left to react with my magnesium oxide. Well, it's in a 2:1 ratio, so therefore there's 0.5 mole of my magnesium oxide present. So nice stoichiometric and mole ratios used in here. Therefore D is my correct answer. 6, a graph for PV against T is given. So it's just for a bit of a section in there, and say which gas gives the graph over the widest range of temperatures and gas. So it's going to be your real gas that behaves as an ideal gas for the longest period of time. Now, you need to also remember what are the basic principles thereof, right? So remember, an ideal gas is perfect elastic collisions. There's no such thing as that. They do not contribute to the volume of a container. So you're looking for a very small gas, a very light gas. You're looking at a gas that does not liquefy in essence. That means a gas that has very few attractions in between them. So intermolecular forces being minimal, actually zero. So the gas that we get to is actually hydrogen, and the second one after hydrogen is my helium gas. Those are the two gases that, for the widest possible range, behave as ideal gases. All right. So theory ZUP A is hydrogen gas. And then the last two questions that you asked was, we have in question number 14, we have silver nitrate that is added to a solution of halide, to a halide ion, and aqueous ammonia is then added. The ionic equations of the two reactions that occur are shown. Okay, so we have the first reaction where my silver ion reacts with my halide, and it forms that solid, whether it's chlorine, that's white, bromine, that is cream, or iodine, that's yellow. We don't know, but that's the reaction it gives a solid. Then if we add ammonia to it, then it is either soluble or insoluble. This, if that silver amide basically forms, where the ammonia replaces the chlorine to it. It's slightly soluble, it happens. All right? Or silver will always react with that. It's the presence of your silver, chloride, bromide, or iodide. It depends whether the color is still there in your precipitate. But there's my equilibrium shown. Now they ask a few things, or tell you a few things. The position of the equilibrium in equilibrium 1 lies to the left when X is your iodine. And that's not really true, because my iodine will form a very nice insoluble solid with my silver. So the reaction will lie to the right. It will form my solid, so that's not true. B is the correct one. We'll look at it now. Let's see. They say increasing the concentration of ammonia causes the position of equilibrium to move to the left. Okay, so increasing the concentration of ammonia. So if we increase my ammonia, we're going to take silver out of my equation to form that. So this means my silver ion concentration and equilibrium will drop, and my reaction, according to Le Chatelier, would like to replace that silver. So my equilibrium will shift to the left. So that's why that's correct. All right. So there's a shifting that happens to it when I add ammonia, and it's true. C, Kc for that would be larger. Well, listen, we don't have our chloride and iodide or my halides being part of my Kc in Kc being products, concentration of my product over reactants. All right, so that's my Kc value in there, and it's not part of it, so it doesn't play a role, whether it's chlorine or iodide. So, and then D, equilibrium 2 is a redox. No, it's nonsense. Ammonia stays ammonia. Silver plus 1 is silver plus 1. So there's no change in any charge. There's no electrons being transferred, so not correct either. Always good to have a look at that. 18. Which substance, when warmed with aqueous ammonium chloride, would produce an alkaline gas? Now, identify the compounds first. Well, ammonium chloride, NH4Cl. Now, note that there are additional hydrogens in this, and it can act as an acid. Why am I thinking that immediately? Well, if an alkaline gas is going to be produced, I'm thinking sort of my NH4Cl moving and producing NH3 plus H plus Cl negative. Right, so there's acid base, my acid in there. Right, so it can do this. But remember, if we're thinking about an acid-base reaction, this is my acid, it will act as an acid, we need a base to react with it. So immediately A is a carboxylic acid, so it's not a possibility. An alcohol could potentially, but it's such a weak acid, it's actually not seen as an acid, so no, it does have that. But it's not a base. It's not a base. It's not going to dissociate with that if I think about it. It's rather seen as a weak, very weak acid. As I said, there's more dissociation with the hydrogen ion. Next year, when you're doing A-level chemistry, we'll speak about that quite often. Ester, no, an ester is not going to react. It can't really react with that. The last one is my sodium ethoxide. So there's actually something like that. And here it can, because this can now, my sodium can be replaced with a hydrogen producing an ethanol, actually producing an alcohol in there. And then ammonia gas is released. So you're looking for the one with a base character in there for an acid-base reaction to happen. Okay, so hopefully that helped a bit. Good luck.